We all learn in basic physics that like charges repel, right? Positives push away other positives. So how in the world can you cram a bunch of positively charged protons into a space that small without the whole thing just exploding instantly? Now, your first guess might be gravity, right? I mean, all those particles have mass, and mass creates gravity, but it's not even close. The electromagnetic repulsion, that's the Coulomb force, is astronomically stronger than the gravitational pull between them. Gravity is just completely overpowered in this fight. So, if the force pushing everything apart is winning, and gravity is too weak to help, there has to be something else. Another force we haven't talked about yet, a secret weapon powerful enough to overcome that repulsion. And folks, here it is, the strong nuclear force. This is the hero of our story. It is, by far, the strongest force in the entire universe. But here's the catch. It has a very short reach. Think of it like super powerful, microscopic Velcro. It only works when two nucleons are practically touching. And the best part? It doesn't care about charge. It grabs a proton and a neutron. Two protons, two neutrons. It holds them all together. This graph is amazing. It's like a personality profile for the force. See that big dip? That shows a really powerful attraction when nucleons are at that perfect sweet spot distance. But if you try to push them any closer together, that's the sharp spike on the left, the force suddenly becomes incredibly repulsive. It's like it has a built-in personal space bubble that keeps the nucleus from collapsing in on itself. Why are certain combinations of protons and neutrons stable while others just fall apart? Take a look at this. This chart is a map of every known nucleus. We've got the number of protons on the bottom and the number of neutrons going up the side. See that narrow cluster running through the middle? That is the band of stability. If a nucleus falls in that band, it's stable. And notice the pattern. For lighter elements, the sweet spot is about 1 neutron for every proton. But as you get heavier, the band curves upwards. Those bigger nuclei need way more neutrons to keep things together. Radioactivity isn't some weird man-made thing. It's a totally natural process. It's just an unstable nucleus's way of getting rid of extra energy and particles so it can settle down into a more stable, lower energy state. The material itself, we call it radioactive simply because it's full of these unstable atoms. Okay, so to really get why a nucleus becomes unstable in the first place, we have to look at the two powerful forces that are competing inside it. For an atom to be stable, its ratio of neutrons to protons has to fall inside this really narrow band. For the lighter elements, a simple 1-to-1 ratio works just fine. But as atoms get heavier and that proton repulsion gets stronger, they need more and more neutrons to act as extra glue from the strong force, to hold the whole thing together. So here's the key takeaway, right? If a nucleus finds itself outside of this band, maybe it has too many neutrons or too many protons, or it's just too big and heavy overall, it becomes unstable. It becomes radioactive. And now it has to decay to get back into that safe zone of stability. Okay, so it's unstable. But what's it going to do about it? Well, an unstable nucleus has a few different options up its sleeve for getting rid of that extra mass and energy. Let's break down the 3 main ways it can do that. First up, we've got alpha decay. This is the go-to solution for really heavy nuclei that are just too big for their own good. To drop some weight fast, the nucleus basically just throws out a chunk of itself, a particle made of 2 protons and 2 neutrons. This chunk that gets ejected is what we call an alpha particle. And since it's basically a helium nucleus, it's pretty big on the atomic scale and has a +2 charge. This makes it highly ionizing. It's like a bowling ball in a room full of pins, really good at knocking electrons off of other atoms it runs into. But because of that, it loses energy really fast and has super low penetrating power. I mean, it can be stopped by a single sheet of paper. All right, next up is beta decay. This is what usually happens when a nucleus has too many neutrons for its number of protons. To fix that imbalance, and this process is super important for things like carbon dating, a really fundamental change happens inside that nucleus. So picture this. Inside that nucleus, one of those extra neutrons just flips. It changes into a proton and an electron. The new proton stays right where it is, which actually changes what element the atom is. But that electron, it doesn't belong in the nucleus, so it gets shot out at an incredible speed. And that fast-moving electron is what we call a beta particle. Since a beta particle is just a high-speed electron, it's way, way smaller and faster than an alpha particle. It's got a -1 charge and is only moderately ionizing. Its tiny size means it can travel a lot further, zipping right through paper but getting stopped by a thin sheet of aluminum. And last but not least, we've got gamma decay. Now this one's different. It's not about changing the number of protons or neutrons. It's all about a nucleus that's just too worked up. It's in an excited, high-energy state, usually right after an alpha or beta decay. It just needs to release that extra energy to calm down. And how does it do that? It emits a gamma ray. This isn't a particle at all. It's a high-energy wave of light. It has no mass and no charge, so it barely even interacts with other atoms. That makes it weakly ionizing, but it also makes it incredibly penetrating. You need thick lead or several feet of concrete to have a chance at stopping gamma rays. So this table here really lays it all out, side by side. You've got the big, heavy alpha particle that's highly ionizing but easy to stop. You've got the much smaller, moderately ionizing beta particle. And then you have the gamma ray, which is pure energy, weakly ionizing but extremely hard to block. 3 totally different solutions to the same problem, instability. And this visual makes that point super clear, doesn't it? You see the alpha particle getting stopped flat by the paper. The beta particle sails through the paper but gets blocked by the aluminum. And the gamma ray? It just passes right through both of them, only getting stopped by that thick block of lead. Okay, so we get the what? We understand the processes. Now, how do scientists actually write this stuff down? Well, they use a special kind of language, nuclear equations. For alpha decay, the math is pretty simple. The nucleus loses 2 protons and 2 neutrons, right? So we just subtract 4 from the top number, that's the mass number, and 2 from the bottom number, the atomic number. The most important thing is that the numbers on both sides of the equation have to add up and balance out. Let's look at it in action. Here we have uranium-238 decaying. It spits out an alpha particle, which we write as a helium nucleus. Now, if you do the math, 238 minus 4 is 234, and 92 minus 2 is 90. You look on the periodic table, and the element with atomic number 90 is thorium. See? Everything balances perfectly. Now, beta decay. This one's a little bit of a head-scratcher at first. Remember, a neutron turned into a proton. So the total number of particles in the nucleus, the mass number on top, doesn't change at all. But because we gained a proton, the atomic number on the bottom actually goes up by 1. A classic example, and one you've probably heard of, is carbon-14, which is used for radiocarbon dating. It's got 6 protons and 8 neutrons. So one of those neutrons decays. The mass number stays 14, but the atomic number ticks up from 6 to 7. And the element with 7 protons? That's nitrogen. So over time, carbon-14 transforms itself into stable nitrogen-14. Of course, scientists didn't figure all this out in a day. It was this incredible scientific journey, starting with a total accident in 1896 by Henri Becquerel. The work was famously pushed forward by Marie and Pierre Curie, and the final, crucial piece of the puzzle, the neutron, was finally found by James Chadwick in 1932. That's what gave us the complete picture of the unstable nucleus.